Heat transfer example problem, internal flow with constant surface heat flux. Air flowing through a 5 centimeter diameter pipe at a mass flow rate of 0.001 kilograms per second is to be heated from 20 to 100 degrees Celsius. A silicon rubber heater with a constant surface heat flux of 400 watts for every square meter is wrapped around the pipe, and then a layer of insulation is added on top. For part A, find the minimum length of pipe required to heat the air. For part B, sketch the mean, surface, and centerline temperatures and heat transfer coefficient versus dimensionless axial distance downstream. Our first assumption for this problem is steady flow of air through the pipe. Our second assumption is constant properties, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our third assumption is that there is negligible radiation for the interior boundary. This is a reasonable assumption for moderate temperatures combined with significant convection at the interior boundary. Our fourth assumption is that there is perfect insulation on the outer boundary of the heater. This means that all the thermal energy from the heater will go into heating the air. Our fifth assumption is that the air is an ideal gas at atmospheric pressure, which will be used to look up properties. For part A, to calculate the length of pipe needed to heat the air, we apply an overall energy balance to a control volume that contains the length of pipe with the heater. This results in a fairly simple equation that can be used to solve for the pipe length. Substituting in values, we get a length of 1.28 meters. Note that for this calculation, we used properties that were evaluated at the mean fluid temperature of 60 degrees Celsius. Also, note that because we assume perfect insulation, this length will be a little shorter than required for the actual conditions, and we would probably want to round this up to account for losses. For part B, before we make our sketches, we will do some calculations to help us determine how they should look. First, we calculate the Reynolds number based on pipe diameter to check the flow regime. Substituting in, we get a value of 1,335, which would definitely correspond to laminar flow. Using the correlations for entry length for laminar flow, we get a hydrodynamic entry length of 67 diameters and a thermal entry length of 47 diameters. Thus, for our pipe with a diameter of 5 centimeters, this corresponds to lengths of 3.35 and 2.35 meters, respectively. For this case, the pipe length to diameter ratio for the heater is about 25.6. Thus, the flow will be all in the entry region, both hydrodynamically and thermally. For our final calculation, we will use the Nusselt number for fully developed flow with constant surface heat flux to calculate the convection coefficient for these conditions. Plugging in values, we get 2.38 watts per meter squared Kelvin. We are now ready to sketch temperatures and the convection coefficient versus axial location. First, for the mean temperature, we indicate that for constant surface heat flux, it will increase linearly throughout. For this case in particular, the mean temperature will go from 20 to 100 degrees Celsius from the entrance to 25.6 diameters downstream. If we continue adding heat at this rate to additional pipe, the mean temperature would continue to increase linearly. Second, the surface temperature will initially begin increasing at a faster slope than the mean temperature. When it approaches the thermally fully developed condition, it will also increase linearly at the same slope as the mean temperature. Third, the centerline temperature will not increase until thermal energy has reached the center of the pipe. Once again, when it approaches the thermally fully developed condition, it will also increase linearly at the same slope as the mean temperature. Finally, for the convection coefficient, for an actual flow, it will start out at a finite value and decrease based on figure 810, part A, in your textbook. If the pipe with heating makes it to the thermally fully developed condition, it will asymptote towards a value of 2.38 watts per meter squared Kelvin based on our calculation.